Hello, I'm Nitin Shah, and this is my presentation on joint encryption and error correction for quantum communication. So the background of this work is related to the noisy quantum channels that we have right now, which leads to a lot of quality issues when you're trying to send a message over a quantum channel. A lot of bits would go in a wrong state, and thus when you measure the qubits, it will end in a wrong translation, thus you will lose some parts of the message. So for that, we need quantum error correction codes. But the problem with quantum error correction codes are that they are very heavy in nature. So you would have to use multiple qubits just to encode one bit of message. So to reduce this overhead, what you can do is come up with a protocol that can do both encryption and error correction at the same time. So you save up some bits while you're trying to distribute the key. So for that, we came up with this integrated protocol where we took the three-stage quantum protocol and integrated it with CSS or Calderbank-Shor-Steane quantum error correction code. So the final output of this work is an integrated protocol, which is first of its kind, and it can do joint encryption and error correction. So by that I mean is if you want to send a message across a quantum channel, you don't need to do the key distribution stage. Rather, you can use this protocol and directly encrypt your message and send it across the quantum channel where the receiver can do all the error correction which is inbuilt to this protocol. So he would not need to do external error correction. Everything is inbuilt in this protocol. So one more benefit of this particular error correction scheme is that it can correct up to 2 bits of error. That means it can correct a phase flip error and a bit flip error at the same time, which no other quantum error correction protocol do. So we have a higher error correction capability while sending a message directly. So you are skipping the key distribution stage and thus saving up some qubits and some time, of course. So we start with the definition of CSS code, which comes from classical error correction. So this is what it looks like. The quantum analog will use get vectors. So to represent a quantum state where you choose two classical linear codes, C1 and C2, and then you translate it to quantum version. So basically, if you're choosing a Hamming code, all the zeros would represent a Z matrix and all the ones would represent an X matrix. So that's how you translate the classical code into a quantum version. Then example encoding would look like this. This is a Steane encoding where the one basis is represented by all the superposition of all the odd one parity basis. So that means you see all of these entangled tensor states. In this, you will notice that the ones are always an odd number and similarly with zero, and it's an equally distributed equipartition of all these states. So now we use the three-stage protocol that how that works is you take your initial encoded bits and you send it to the receiver. The receiver, before you send it to the receiver, you put a rotation on all the bases. The receiver will now put their own rotation, which is UB, will send it back to you. You will remove your original rotation and will send it back to the final user who can remove his or her rotation and thus get the original message back. So the rotation matrix would have a form like this. It's a tensor product. So what it's doing at the end of the day is it's taking all of these individual ones and zeros and putting a rotation on it. So yeah, and then this is how it works. Then the shifting process, if you are doing a key distribution, you can use this process. If this process is not done when you're trying to directly send a message, then this is the error correction process where Alice chooses a code word. It means a string from the C1 and C2 that we earlier discussed. Then she would declare, uh, so the code word is VK, then she would declare X minus VK. So X was the qubit that she sent. VK is the bits that she chose from here. So this is an XOR operation. Then Bob can directly find the error, what he had using the error correction methods. Then he can recover the VK, which can act as a key, or in the case he can recover X directly too, because well, they will have the same message. So this step is for key distribution as well. So we just proved up that the protocol can do both key distribution and direct communication. So some of the steps are mostly for key distribution, but If you're not using it for key distribution, it's equally good for messages because you won't be doing this two steps here. Just be the error correction by Bob, which is directly inbuilt. So it will use ancillary qubits to find the error syndrome and then correct it using Z gate or X gate and so on. So this actually bounds the rate of our code. So basically how efficient the code can be. So for a given NKD code, this basically means if you have k qubits, you'll encode it in n qubits. So here, if we look at this example, it would be a 7-1 code. 712, the distance means how much it can correct. So it's a 713 code. So that means it can correct up to 2-bit error. So based on that, this is the code rate that we have defined. It comes from Washamov bound for linear codes. And yeah, this work has been published in Nature Scientific Report recently. There's a paper link and my LinkedIn. Feel free to reach out to me with any other question that you might have. Thank you.